I'm Bruce Bjornstad. Thank you for coming tonight. I'm going to spend the next hour or so with you, sharing with you the Ice Age floods from an aerial perspective. Okay, the scale of the floods was so huge, as you know, and it covered such a wide area many times over and over again. It's really hard to appreciate from the ground. So really to get up in the air is the best way to really see these features, the scale of these features, and appreciate the power and magnitude and the frequency of these floods that occurred over and over again. So anyway, this is an image of Dry Falls, and I'm sure a lot of you have been here before. If you have been there, you've probably gone to the visitor center, which is over here. It's a grove of trees, and there's a little the visitor center is right there, and there's Highway 17 coming up the Lower Grand Coulee. And when you go out to Dry Falls and you look out across the falls, what you're basically seeing is this. You're just seeing a very small part of Grand Coulee and Dry Falls. Dry Falls is there's more falls over here on this side, and then it extends for another 3 miles to the east. So everything you can see in this picture was under hundreds of feet of flood water, 300 feet deep. The water was 300 feet deep when it went over the falls, and then it was 600 feet deep when it got down here into the cataract. So there are at least 3 flood sources that we know of. The main one we're going to talk about tonight is Glacial Lake Missoula. This occurred as many as 100 times during the last glacial cycle. But there are 2 other lakes that generated floods. Another flood came out of Lake Bonneville down here about 18,000 years ago. And it got into the Snake River, basically followed the Snake River down to where we are in eastern Washington, and then out to the Columbia through the gorge. That only happened once about 18,000 years ago. There's another lake up here called Lake Columbia. And again, that only probably drained once, maybe at the very end of the last ice age, Glacial Lake Columbia. So we're going to focus here on Glacial Lake Columbia and the floods that generated the channel scabland. Here's kind of a simplified picture showing you the elements that go into describing the floods. Here's the main culprit. Up here is Glacial Lake Missoula up in western Montana. There's the ice dam that came down the Purcell Trench, blocked the Clark Fork River with 3,000 feet of ice. Clark Fork River drains this area, so when the water from Clark Fork River tried to escape, it was all backed up behind the Purcell Trench. And downstream of that, we have another lake called Glacial Lake Columbia that formed behind the Okanagan lobe during most of the Ice Age. And then we have the channel scabland, which was the area downstream that was flooded during these floods. So when that ice dam failed, all that water, 500 cubic miles of water, drained out in a matter of a few days or less. It hit Glacial Lake Columbia during most of the flood up vents, hit Glacial Lake Columbia, and it didn't take much more water from Lake Columbia to spill out across the channel scabland because the Okanagan lobe was in the way, blocking the Columbia River. That diverted all the water out into the channel scabland. So the last floods, we think, were about 15,000 years ago from Glacial Lake Missoula. And then the earliest floods, we think, go back to 1 to 2 million years. The floods were mainly the idea of this individual, J. Harlan Bretz, who back in the early 1920s just was intrigued by some of the unusual landforms that we have in eastern Washington. So he was working in Seattle at the time, and back in the Midwest. And he would, in the summer, he would make trips out here to Eastern Washington and look at the evidence for what he didn't know what the cause of these unusual landforms were, but he spent several years working here. And in 1923, he published a paper, and his conclusion was the only genetic interpretation yet proposed, which is inherently harmonious and which fits all the known facts, is that of a great flood of water. So this was his outrageous hypothesis that he published in 1923. And then his hypothesis changed somewhat over the years, but he basically had the right idea that there was a huge flood or floods that created the Channel Scabland. This is a map he produced in 1923 showing channels in Eastern Washington. Canyons in the Scablands are multiple and anastomosing, amazingly so in some tracts. Deep canyons and shallow ones uniting and dividing in a labyrinthine fashion about bare rock knobs and buttes, unlike any other land surface on the earth. He did this all from the ground. He never got up in an airplane. I mean, he did it all from the ground. And compare it with a satellite photo that was taken in 1972 from space. You can see the channels of the Scabland. You perfectly match those from space as the ones from that were mapped by J. Harlan Bretz. So we're going to zoom in now on the ice lobe, the ice dam, or glacial Lake Missoula. Here's the western edge of glacial Lake Missoula. It was up to 2,000 feet deep here, where it was backed up behind the ice dam. The ice dam itself was another 1,000 feet high. So the floods from Lake Missoula, or glacial Lake Missoula, didn't drain by water going over the top of the ice dam because it was much higher than the lake itself. But something what did happen, the ice probably floated the ice dam, or fractured it in such a way that the water from the lake could start to make its way through the ice dam and eventually break apart. So we're going to zoom in now on this image at the very western end of glacial Lake Missoula. This is what it would look like. This is an actual photograph, but it was doctored by David Bennett. David Bennett produced this, and he's a pilot. He flies around, and he actually had someone draw in the ice dam and icebergs and things in the lake itself, where the ice dam used to be. This is looking west towards the ice dam, and that ice you can see up in the upper left was actually ice that moved up the Clark Fork River. There was another lobe of ice that went down into Lake Pend Oreille. So altogether, that ice dam was almost 30 miles long from this point down to the mouth of Lake Pend Oreille. So it's a huge ice dam. So it really took a lot of water and force to break up that ice dam. So how do we know there was a Lake Missoula? You know, it's obviously it isn't there today, but you can actually see these strand lines moving up the sides of the hillsides around Missoula, Montana. This is Mount Jumbo, and the strand lines here are ancient lake levels for Lake Missoula as it was growing and shrinking during its existence. The highest strand lines go up to 4,200 feet elevation. And that tells us how high the lake must have gotten. We don't see any strand lines above that. And that 4,200 feet is about 1,000 feet below where the top of the ice dam was that I showed earlier. Here's a place called Markle Pass within glacial Lake Missoula. This is a place where the valley narrows down. The lake was much deeper than Markle Pass, but as the lake was draining, it was eventually got funneled through Markle Pass. As it was dropping in elevation. And as it did so, it sped up faster water, Venturi effect, actually creating scabland in Markle Pass. And as you can see, there's a tongue-shaped flood bar that formed just downstream of Markle Pass, made of deposits that were carried by the lake water as it was draining through the pass. And then on the lower right, you can see some faint giant current ripples. And here's another images of giant current ripples that formed as the lake was draining very, very rapidly. If you look at, you can't see it here, but if you look up close on these ripples, you'll see big boulders of rock making up the ripples. So the water creating these ripples was moving very, very fast to be able to move large particles like boulders within these giant current ripples. Here's the outburst area for glacial Lake Missoula. There's the ice lobe coming down. So this is the lower end of the ice. The upper end of the ice was way up here in the Idaho-Montana border. So it was 30 miles from there all the way down to here to the mouth of Lake Pend Oreille to where the ice dam was. And as that ice dam broke apart, that water would all drain down through the outburst plain into the Rastern Prairie and eventually down to Spokane. Near Spokane on the upper right. This shows the area without any ice. And there were floods coming down from Lake Missoula when there was no ice blocking the Columbia or the Spokane rivers. And when that happened, floods from Lake Missoula would actually just go down Columbia River all the way around the Horn of Columbia and then down past Wenatchee this way. We have evidence for some floods going that route. But at other times, and most times, and especially later, the Okanagan lobe came down and blocked the Columbia River at the head of Grand Coulee in the upper left. And there was another lobe of ice called Columbia lobe that also blocked the Spokane River. So there were multiple ice lobes coming and going that would control the amount of water, flood water draining through the channel scabland. So there's a whole set of diagnostic flood features, and we divide these into erosional features and depositional. I'm going to talk about a lot of these in the rest of the images, so I'm not going to go through each one right now, but you can see there's a long list of characteristic features of these ice age floods. So first of all, we must talk about the Palouse Hills, which are these rolling hills of windblown loess that occur in eastern Washington. These hills once covered the area of the channel scabland, but the scabland, when the floods came through the scabland, they eroded away a lot of the loess, the Palouse, down into the bare basalt bedrock. But off to the east, I'm including this image so you can see the character of these Palouse Hills. Are very rolling, gently rolling hills of this fine grained sand and silt that we call Palouse loess. So this is what it looked like before any flooding of eastern Washington. All of the scabland might have looked like this 2 million years ago, or 1.5 million years ago. And this is what they look like today. These Palouse Hills, you can see most of it's been eroded away, and there's been channels carved out by the Ice Age floods, and these hills have been streamlined. You can see they're bullet-shaped hills that were streamlined by these Ice Age floods. They go down, and it goes down to basalt bedrock, is at these flat areas in between. Here's a good example of a streamlined island. Got a very steep brow in the front here, and then it tapers off in the back. Floods were coming down from the lower left, creating scabland channels on either side of the island. And here's another streamlined island looking downstream. Here's the front, the steep prow in the front, and the tapered tail in the back end. But you can see how the floods must have gone up over the top of this island and spilled over and carved another channel. You can see there's a cross channel here of these floods. And then here's another example. This is looking upstream. Here are the steeper prows or fronts of these streamlined islands. And you can see where their floods have eroded down to the basalt bedrock on either side of these islands. And there are potholes. These are huge potholes. There's my friend Tom Foster, rest in peace, standing next to a pothole in East Lenore Coulee, adjacent to the lower Grand Coulee. Deep Lake, which is also by Dry Falls, some huge potholes in that area, deep, hundreds of feet deep, 100 feet wide, 100 feet deep potholes. And over on Bagpack Bench along the Columbia River, more potholes. And rock blades, these are places where the floods eroded laterally or on either side of these blades. You can see this blade's 50 feet, easily 50 feet tall. There's scabland on either side. And Potholes Coulee over on the right is another place. These blades of basalt are places where the floods didn't erode all the basalt away, apparently because the power of the floods split into two streams with going parallel to each other. And the area in between the two streams didn't erode as much, leaving behind these blades of basalt. There's Dry Falls, and there's one cataract, there's Dry Falls, and there's another cataract over here. Umatilla Rock is the blade of basalt down the middle of Dry Falls. And then Frenchman Coulee over by Vantage along the Columbia River. Another pair of cataracts, recessional cataracts with a blade of basalt down the middle. This is a recurring theme over and over again in these in the flood eroded basalt terrain. And giant current ripples. Okay, we've talked about a bunch of erosional features. Now we're going to talk about some depositional features. Giant current ripples. These are two pictures of the same area near Odessa. Here's a highway, State Route 28 down there in the bottom for scale. You can see the size of those ripples. They're easily 100 feet apart, 50 feet high. Sprague Lake on the way to Spokane. If you've ever, anybody who's driven to Spokane, you go by I-90, you actually go right by Sprague Lake and these giant current ripples, but you can't see them from the ground. You have to get up in the air to see them. And Wilson Creek is another great place. Here you can see there are multiple sets of ripples that are on different flood bars, different surfaces, which is unusual. We can tell the direction of flow of these ripples based on the asymmetry of the ripples. Here you can see that on the ripples, these dark areas are steeper areas on the downstream side, and then on there's a gentler upstream side of these ripples as well. So you can tell the direction of flow by the asymmetry of the ripples. Ice rafted erratics. These are also carried in by the Ice Age floods, floating in icebergs, probably mostly coming from the breakup of the ice dam in northern Idaho. This is a photographer from National Geographic photographing a big erratic that Gary Kleinknecht found, actually, and turned us on to back around 2000. along Badger Coulee. Another erratic along the White Bluffs. Columbia River off to the right. You can see it's a few hundred feet above the river. And this boulder, again, is a piece of argillite. It's angular. Most of the erratics we see are angular, subangular. This one's definitely angular. And it's made out of argillite. The closest place we see argillite is about 200 miles away, up in northern Idaho. Here's one in Cow Creek. There are very few erratics, especially erratics of this size in the channel scabland. The Cow Creek is in the scabland, and it's surrounded by basaltic, severely eroded basalt rock. But apparently survived because it's so big, and the topography in this area is fairly gentle, so the floodwaters weren't very thick or very deep, and it probably this boulder was so big that it probably just got grounded in the shallow floodwaters. And remember, it takes Ivor Husa, who's here, actually calculated the amount of ice it would take to float an icebergs like these. And he calculated it would take an iceberg 10 times the size of the erratic to float it. And maybe more, probably more. It takes a lot of ice to float boulders this size. And here's one on the side of Alula Gap, the west side. Again, it's angular, like the others, and that's a sign that it wasn't brought in by running water, moving water. Otherwise, they'd be rounded. But when they're angular, they're granodiorite, which these three are granodiorite. The ones over on the left, and all point to the fact that these are ice rafted erratics. Okay, so we've talked about a bunch of the features. Now let's look at some of the landscapes that were carved out by these ice age floods. Some of the more well-known ones. There's dozens of them out there, and I've documented, probably 100 flood features in my books. But I'm just going to talk about a few of the most important ones. Grand Coulee is the big one. That's kind of the destination for a lot of people. In the upper Coulee, we have Steamboat Rock. Before 1950s, there was no lake here. This is Banks Lake. It's a man-made reservoir. So it's just mostly a dry coulee with scabland features all through it. And over down here is the lower Grand Coulee. Here's that Great Blade looking at it from the side. When you're driving along lower Grand Coulee and you look up at the Great Blade, you think it's just a massive wall of basalt that goes for miles. But in fact, this blade of basalt is only 10 to 20 feet wide at the top. And then the Coulee monocline is an area where the basalts have been folded over long before the floods, creating these hogback islands you can see here. And then Dry Falls, of course, is in Grand Coulee. This is the most popular spot in the Grand Coulee. I included these to show these giant grooves in the basalt. These are this is looking downstream in the lower left, looking upstream in the upper right, and you can see the wonderful grooves that were carved out in potholes along the top and behind Dry Falls. Drumheller Channels is another really unique spot and beautiful. It's Columbia Wildlife Refuge area. It's open to the public. It's closed certain times of the year to protect some of the wildlife, but starting around this time of year in March, it opens up for hiking and fishing and lots of other activities, bird watching. So one of the main draws of Drumheller Channels is its amazing basalt columns. Okay, these are columns of basalt from the Elephant Mountain lava flow. That's about 10.5 million years ago. And At one time, it was one continuous layer that spread out for hundreds of miles or dozens of miles. But when the floods came through, you could see how they've eroded the scabland out and behind it. But then when they came through this area, they would preferentially pluck out the basalt columns very easily. The power of the floods was so huge that it easily picked up and pulled out these columns of basalt and transported them downstream. Here's a streamlined island of basalt. So here's the upstream side here, and it's pointed prow, and it's surrounded by these beautiful basalt columns, like you see here. These basalt columns continue all the way across, I'm sure, except they're covered in the middle. They're covered over with a younger entablature basalt, so you can't see the columns underneath, but you can definitely see them around the margins where the floods were most erosive. And this is showing the direction of flow of the water coming from the north out of Grand Coulee. It hit this island head on down on the lower right, and it actually carved a secondary channel across the top. You can see that arrow pointing off to the left. That's a secondary channel. Here's a closer up view of of those basalt columns. So yeah, these columns are 5 or 6 sided, hexagonal, pentagonal columns. And they're 50 feet tall. They go straight up and down. And these are cooling fractures. As the lava was cooling, the interior of it stayed molten for a lot longer time. And as it cooled very slowly, these cracks would propagate downward within the basalt flow as the volume decreased from the cooling of the lava. Blues River Canyon is another spectacular and unique feature. In this image, we're kind of looking upstream along the Blues River Valley up here, and it occupies a coulee called Washtuckna Coulee. But at some point during the floods, the floods were so deep and powerful, they actually carved a new channel across the divide with the Snake River, which is about 10 miles to the south. And when that divide got crossed by the floods and carved a new channel for the Palouse, it hijacked the Palouse River, and you can see how it takes a sharp left turn where that yellow arrow is, and from there it heads down straight towards the Snake River Canyon. The Washtuckna Coulee is still there, but it's totally dry. It's been cut off from any water from the Palouse River. It has been used during Ice Age floods, but never again by the Palouse River. This is the lower end of Palouse River Canyon looking up towards Palouse Falls. And then here's a dramatic photo just above Dry Falls, or just above Palouse Falls, looking to the north. And you can see there's the Palouse River off to the right, draining down. But all those other channels that you can see off to the left are totally dry, except for a few small lakes. So that whole area, all that landscape you can see here, was all underwater, draining floodwaters at the same time. Devil's Canyon. How many people have been to Devil's Canyon? Know about that place? Okay, yeah, a lot of people don't know about it, and the more people are finding out, because it's really hard to find, first of all. And you kind of have to know where it is. And there's no sign pointing how to get there, but if you do find it, it's really a gem. You can see this is looking upstream towards Colotis, the town of Colotis, and Washtuckna Coulee are up here. This is looking downstream towards Monumental Dam, just downstream, and the Snake River down here. You can see how the floods spilled out of Washtuckna Coulee at Colotis, and they carved a whole new channel for Ice Age floods down Devil's Canyon. This canyon is very straight and narrow, And it's exactly parallel to the Palouse River Canyon, that long, deep canyon, Palouse River Canyon is exactly parallel. And that's due to these fractures, these tectonic fractures that were in the basalt. And then when the floods came along, they preferentially eroded out the weaker broken rock along these fractures, which is why we see these straight canyons today. And some of the floods actually went over the top as well. They went down the Devil's Canyon this way, but they also spilled over from Washington Cooley from this direction, overtopping the sides of the Devil's Canyon. Okay, West Bar. This wasn't we don't think this was a flood bar created by a Missoula flood for a number of reasons. But we think it was probably glacial Lake Columbia flooding after the last Missoula flood about 14,000 years ago. Another possibility is, or it could have been a subglacial flood coming down the Okanagan Valley, which has been getting a lot of traction lately, subglacial floods with Nick Sentner and his series. We don't know which of these or either of these scenarios is actually right, but we know it couldn't have come from a Lake Missoula flood because the Okanagan lobe was in the way. There's no way the water could have gotten coming down the Columbia River. There's no way the water could have come off the scabland and created these ripples that you can see are definitely oriented such that the water is coming from the northwest across the bar this way. Wallula Gap is another major important feature. This one's nearby. It's only 20 miles away from here. This is an image painted by Stev Ominski, my friend Stev, who I sent him a picture and a photograph taken from an airplane. I think you were with me, Gary, when we took the picture. And we took this picture and then sent it to Stev, and he painted in where he thought how the water might have been flowing through Wallula Gap, and I think it's fairly accurate. Today, the Wallula Gap is only about this wide down here, but you can see during the floods it spread out on either side, both east and west sides of the gap. It spread out into the creating new scabland off to the upper reaches of the Wallula Gap. Now here's a photo taken from the air. You can see this. There's several intersecting channels up there of where the floods eroded the top of the western side of Wallula Gap. And then on the east side of the Wallula Gap, we have the same thing. There's the river itself and the gap, but you can see this is all scabland. It's all areas that have been stripped away and eroded by ice age floods. And in this image is actually underwater. You can't even see it in the water that Stev painted. He didn't paint the maximum water level. It actually went up higher and probably covered almost all the hills on both sides of the gap. But for effect, to be able to show the power and the force of the water, he included these side areas in his image. So behind Wallula Gap, there was twice as much water coming in the gap. The gap is only 2 miles wide. Floodwater spread out for up to 100 miles across the channel scabland, and they all converged onto this one little opening at Wallula Gap. With all that water converging on this one little opening, you can imagine what happened. The water had to have backed up. There was probably twice as much water going in the gap that could actually go through at once. So the water backed up, created a big lake. We call it Lake Lewis. It's a temporary lake. It was probably only here for a few weeks, only as long as it took for all that water from Lake Missoula to drain out through the gorge and out to the Pacific. So floods were moving, coming down the Snake River. They were coming down from the north by Grand Coulee, and they were coming down Columbia River. by way of Wenatchee and Quincy. And the deeper the water, the darker the blue, and the shallower, the lighter the blue. So you can see how the waters were much deeper out in the middle of the basin. And then there are a lot of icebergs being carried down with the floodwaters. And you can see how they would have floated around in Lake Lewis in the bottom image. So there's more images I added to this slide. And you can see we added rhythmites, which are these slack water flood deposits that were deposited within the back flooded basins of the Walla Walla Valley and the Yakima Valley, and even all the way up into the Snake River. And then there are also ice rafted erratics being carried, as I mentioned, in icebergs floating around in the lake. And we see a lot of these erratics, especially in back flooded valleys, like at Snake River, or I mean Rattlesnake Mountain. So Rattlesnake Mountain, this is the same Rattlesnake Mountain that's here in the Pasco Basin. About 10 or 15 years ago, I worked a few years mapping erratics and berg mounds on the within the Rattlesnake Mountain area, and I counted over 2,000 of these erratics. I located where they were on a map and the type of rock and that kind of information. Here's just two examples of some of the 2,000 erratics that I found on Rattlesnake Mountain. The upper one is argillite. Again, we can trace this back to northern Idaho, and the lower one is a piece of granodiorite. 3/4, about 75% of all erratics I mapped were granodiorite or granitic rocks. And these argillites only make up about 10% of all the erratics. There are quartzites also that come from the belt group, similar to the argillite. And we also have what we call berg mounds. Okay, a lot of you may not understand, probably a lot of you don't understand what these are, but they're mounds of ice rafted debris within Lake Lewis. And the map on the left, there are all these the blue diamonds are berg mounds, and all the smaller red dots are isolated erratics or groupings of erratics. But on the right, you can see these berg mounds beautifully show up on LiDAR. The special imaging technique strips away all the vegetation down to the bare ground, and you can actually see these bumps in this landscape, which is a mile wide, are berg mounds. And here's what they look like from the ground. They're not very big, but they are definitely round, and there's a lot of them, hundreds of them. Okay, now we're moving down into the Columbia River Gorge, and I'm going to show you some places you've probably never seen from ground level here. When you drive down Columbia Gorge, you go down to I-84 on the Oregon side. If you look off to the south here at Philippi Canyon, you can see an interesting canyon-like feature over on the left, but you can't see most of what else is up here on the upper part. And this is a place where the floods spilled out into Philippi Canyon, spilled over the divide and into the John Day River. And you can actually see the John Day River up there in the top of that photo. That there's a little piece of it up there. And then a few miles down, the floodwaters going down over the divide into the Philippi Canyon, and they join the John Day River and then reconnected with the Columbia River a few miles downstream. But the floodwaters were so deep, they had to have been 1,100 feet deep to get up and over this divide. So that's things like that. That's how we figure out how deep these floodwaters are, as we look through these spillover channels. And the elevation of those spillover channels was once the high water mark for these floods. Okay, here's another place I call Celilo Scabland, and I-84, same highway, on the Oregon side going down. I don't know how many dozens of times I drove down here going to Portland and looked up and saw this wall of basalt on the side. And it wasn't until I got a drone and I started driving around up onto in this area that I realized this is all scabland. It's in the middle of the Columbia River Gorge. And you can see how the floods scoured out these fractured, tectonically fractured cracks again, similar to what we see in the scabland. There's potholes, rock benches, all sorts of other flood features, scabland features up here on this bench. And then Celilo Falls, which we can't see anymore because it was flooded under water from Lake Celilo behind the Dalles Dam in the gorge. But before it was flooded, you could actually see these huge, deep, parallel grooves eroded into the basalt behind Celilo Falls. And since then, people have gone out after the lake was flooded. People have gone out in a boat and actually did bathymetry and reflected off the bottom, the lake bottom, to get another image of these grooves. And you can see they're parallel, deep grooves, very similar to what we see behind Dry Falls. So these are all flood features, scabland features that are actually still visible in the gorge. You just have to get up high or scuba gear to actually see them. Okay, so now we're going to move down into we've gone through the gorge. We're going to go down into the Willamette Valley. And when the floods came down the gorge, they entered the Portland Basin and spilled south. And a lot of the water went straight north through the Kalama Gap, which was another constriction, causing the water to back up behind Kalama Gap because all the water couldn't go through at once. So, but the water backed up into Lake Allison all the way down to Eugene. And it was carrying lots of icebergs, I'm sure, with erratics, ice rafted erratics. The first one I want to show you is Bellevue erratic. This is what it looks like from the air. The circled Bellevue erratic in the upper image is 300 feet above the valley floor, above the floor of the Willamette Valley. And then the one on the lower left is a close-up of that same erratic. It's also argillite. It's one of the 10% of erratics that are argillite that I've seen. We can trace that argillite again all the way up to northern Idaho, and there's a quarry in northern Idaho that I got a picture of, and the rock wall in the foreground is all made up of argillite coming out of the quarry behind. And Willamette meteorite, up until about 20 years ago, nobody really put things together and realized that it probably is an erratic. Before that, people thought it was just a meteorite that fell on the earth. But there's no crater where they found this meteorite. There are other pieces of granite or other granite rocks nearby around it. And it's iron nickel meteorite, discovered in 1902, 15.5 tons. It's the largest meteorite found in the US. And it's presently in a museum in New York. Can't remember the name of the museum, but it's one of the big museums in New York where it's stored, and you can actually see it there. So why do I think it's an erratic? I think because for one thing, there was no crater. There's other granitic rocks nearby, meaning there probably is other erratics. And if you look at the hydraulics of flood water coming in to the area of the meteorite, you see the water was moving out of the Portland Basin. It was heading south and west towards the Willamette Valley. And as it did so, it eddied around in these smaller tributaries coming in from the sides. So everything in blue was underwater, floodwater. Everything in brown was above the level of the floods. That's 400 feet elevation. And the Willamette meteorite is right at that boundary between the lake and the dry land. And there was the fact that there's probably eddying currents going on would have pushed that iceberg and its meteorite off to the center of that island, that brown island, via the floodwaters moving in and circulating and back flooding into that area. All right, so I'm just about done here. I'm going to put a little shameless commerce in to the show. I have a YouTube channel that I have posted a lot of videos using the drone. I've over the past 10 to 15 years, I've owned 3 different drones, taken lots of pictures and video, and posted a lot of what I call Age Floodscapes on YouTube, with using mostly the drone. And I have a couple guidebooks, the written one in 2006, the other one a little over 10 years ago, on the northern reaches. The one on the left is for the mid-Columbia Basin for this area. The co-author was Eugene Keever with me on the second book on the Scabland. And there's a book published in 2021, picture table type book, color photographs of a lot of the features I've showed you tonight are in the book, plus many more, 180 pages. And that can be purchased at springer.com or amazon.com. And there's Stev, the guy that does all these great paintings of flood features. Okay, with that, I'll answer any questions. Yeah, Dave?
Is it a meteorite or not? Which an erratic, you're saying?
It's both.
Both.
It started out as a meteorite and it later became an erratic. Once it fell into the ice, it was embedded in the ice lobe, probably up in Canada, British Columbia. Then it was brought down in the ice to where the ice dam was. And then
Second question. Thank you. The Saliva Falls is behind what dam?
I think it's Lake Celilo.
Lake Saliva, behind what dam?
The Dalles Dam. I think it's the Dalles. Yeah,
It's still there. It's
right.
it's
Yep.
covered over.
Yeah. Yep. Yeah.
Online, it's asking what was the depth of the Willamette Valley deposits? What was the depth?
The depth of the water in the Willamette Valley was 400 feet. No, wait a minute, 300 feet. Because the floor of the valley is about 100 feet. So you subtract 400, you get, it was 300 feet deep.
When J. Harlan Brett was putting together his hypothesis for what was going on at conferences, other geologists, putting down, they didn't buy it because he couldn't answer the question, where the water come from. The fellow named Pardee could. Did those two collaborate ever?
So the question is, there's Pardee and Brett's, and they had conflicted on where they thought the water, or didn't know where the water came from. And Joseph Pardee, who worked for the USGS, published a paper in 1910 documenting the existence of Lake Missoula. And it wasn't until 1942 that he actually tied it to the floods. And Brett's knew about it too as early as in the 1930s. He knew about Lake Missoula, but he thought the ice dam was so far away. I mean, the lake was so far away that there was no way you could get the water over to the Scabland. But later in the 1950s and 60s, he did finally buy off on the fact that it was Lake Missoula. And Pardee didn't want to he didn't shout it out. He didn't push his ideas, because he was working for USGS, and other members of USGS didn't agree with that theory. And so he was trying to not create waves. Yeah. Yep.
Bruce, there's more than one, how many floods were there?
How many, the question is, how many floods were there? That's a complex question because there were so many different floods at different times, and they weren't always going at the same frequency. There were previous ice ages. We have solid evidence that there were floods at least 1,000,000 years old, going back 1,000,000 years in the scabland. So they could have started as early, they could have started much earlier during the beginning of the Pleistocene, the Ice Age, which goes back to 2.5 million. The evidence for multiple floods is mostly from Lake Missoula. And those are, they've counted up to 100 separate floods from glacial Lake Missoula during the last glacial cycle. And that was only, I mean, that was 14 to 20,000 years ago. But there were many, many floods before that. And we don't know the frequency or nearly as much about the older floods because the evidence is either buried under younger deposits or it's been eroded away and erased. So it's a difficult question to answer, but that's kind of where we're at. Yeah.
Bruce,
Yeah.
do you care to elaborate yourself on what Brett's original hypothesis was? He saw these water deposited features in the mid-Columbia, but there was an orthodoxy back then that there was a tremendous sea level rise. So he thought there was an inland sea, and that idea prevailed for a while until, oh yeah.
Well, yeah, the question is, it's not a question, but Brett's at first and early in his work in the scabland and Washington in the late teens, he started out on the west in the Columbia Gorge and was working his way east. And he thought he saw evidence for marine advance. And it turns out those were actually flood deposits. He was seeing erratics. And once he started getting up in the scabland, he realized that the water was all coming from the north and east. And it wasn't coming from the west, from the ocean. And he doesn't talk about that paper as much as he does his more recent work. I think he would have liked to have seen that paper disappear, but
Well,
that's
back in the day, there were geologists back east who were seeing ice age features and attributing it to a sea level rise on the Pacific or the Atlantic. And so it just seemed it had to have happened here, yes? But
sea levels. Yeah, sea levels do go up and down, but during the Ice Age, sea levels were 300 feet lower than where they are today. So it's just the opposite of what you want. Yeah. Yep. Okay, I think I'll finish there and thank you all for coming. Yep.